Recording is rolling. It is Tuesday, September 27th. All right, and activity I have lined up for you guys today is very non-frame. Right. So I need to tell you guys what that is, what the purpose of it is, and get you guys set up back in the lab area. So you guys can be back in the lab area most today. All right, so we just got news a while ago that school is closed next couple of days. So surprise. I did have all these activities lined up for this week. We're gonna have to postpone all these things. So that's okay. We'll do it. I hope to see you guys on Friday. I don't know. We'll see. Time will tell. But today, let's just focus on very non-frame and yeah, and kind of see what happens from there. All right. So I think probably a really good way to explain this is to switch my screen over and show you guys an actual model of what this thing is, and then tell you guys what it's trying to solve. Okay. So do you guys see like a map? Okay, so I see a map. Oh, I see different objects on this map. Do you guys see 4 pulleys? Pulley, right? And look at that factory in the middle. It's some like cardboard cut out of a factory. I see that. Right now, what's kind of hard to tell, but I'll play this so you guys can see this in motion here in a minute, is that this factory is connected by strings, and each string is wound around a pulley. And then this map has holes in it where the strings hang down, and there's like a lab weight. Right? You guys can imagine that, right? Okay. In fact, if you want to sort of see the model, you can look back behind you guys at those lab tables. You guys see those red pulleys, see some strings, see some lab weights hanging down, right, from earlier classes, right? Which is pretty much that right there. Right? And then if you just threw a map on that lab table, you would have exactly what's going on here. Okay, so what is this supposed to solve? What's the deal with this? So imagine that you are a CEO of some company, and you have to build a factory that's going to make, let's say, pencils, right? Pencils, and this pencil has different resource inputs. So say we need some lumber to make this like wood body of the pencil. Maybe we need some graphite to make the part that writes. Hey, maybe we need like some mine to get this metal bit right here. What's this metal bit called? I don't know. It's something I forget what it's called. Anyway, so we need to make that too. Let's just call it copper. Let's say it's like a copper mine to make that bit. Right. So we have all these inputs, and then we're gonna at this factory, right, construct these pencils out of all those raw inputs, and then ship them to some town. Right now, the transportation costs for each of those material inputs, and then also for the final product that we're shipping out to some nearby town. Right. Well, there's some transportation costs associated with each one of those. Right. And maybe I have a question of like, where do I want to build this factory? Ooh, you guys see where this is kind of come together? Right, it's fit in this model with this map and this location, this factory. It's like hovering, strings, pulleys, right? Hey, do you think maybe there are higher transportation costs for some of those materials than others? Like, for example, the wood, say the lumber that's coming from the forest to build the wood body of the pencil, right? Maybe that's relatively expensive because it's kind of bulky to transport it. We know that whatever wood we end up using, a lot of it's going to be shaved and thrown away. So it's even more massive than would be necessarily just to build the pencil, right? So maybe for a number of reasons, it could be really expensive to transport the wood. But how about the finished product, like the actual pencils? Like once you've made the pencils, you can put them in, you can package them in these nice, convenient rectangular boxes that stack really nice and neat. Maybe it's relatively easy to transport the actual boxes of pencils. You guys can imagine that, right? Right. So from that point of view, let's just for simplification narrow it down to that. It's relatively expensive to transport the wood and relatively cheap to transport the final product, the pencils. With that in mind, do you want to build your factory closer to the forest or closer to the town? Closer to the forest, right? Because again, if it's really expensive to transport the lumber, if your factory is pretty close to the forest, then you don't have to transport that wood very far. Right? It's just like, boom, it's just next door, right? And then it's relatively cheap to transport the pencils. So the factory could be a long way away from the town, and that doesn't really matter because it's really cheap to transport from there, right? That kind of makes sense, right? But hey, maybe we have multiple inputs going on, maybe multiple towns we're transporting to also, possibly, right? So we're going to answer the question of where is the optimal location for the factory? Like, can you imagine there's some latitude and longitude, right? The optimal location of the factory using physics. And remember I told you guys that there's lab weights hanging down on the underside of the map. You can't see the lab weights. They're hanging underneath the map, right? Tied to strings. The lab weight is going to be proportional to the transportation cost. So for example, if it's twice as expensive to transport the lumber as it is the final pencil, then you might have a lab weight that's twice as heavy on the forest compared to the town, right? That makes sense, right? And then you have all these inputs and outputs, and then there will be a natural equilibrium place that will tell you exactly where to build that factory, okay? You see that? So let's put this in motion. Let me rewind this. Actually, here's a good shot here, right? You can see underneath the table. You guys see that? Right? Look at that. Right? You guys are doing that pretty much, right?
The factory would go towards Utrecht. That would be its optimal location then.
Especially these Dutch cities here.
The optimal
Look at that. So you guys see as you change the transportation costs, that factory sliding around, look at that, right? And it sets up these natural equilibrium points. All right, so let's switch back over to the screen. So I can show you guys the classroom version of this. Okay. So I have a page I'm going to give you guys. You guys can have one of these pages per team. So you don't have this in your hands yet, but when you eventually get this in your hands, I've even simplified this a little bit more. So let's just say, so we're building pencils, and let's just say there are really two resources we care about: the wood and the copper. Let's say wood and copper. Right? Of course, so things too. We're going to ignore that. Okay? And then we have the final pencil. And each of those might have a transportation cost. Now, my first example up here, I've weighted them all equally. So I said it's equal cost of transportation for the wood and the copper and the final pencils, right? Okay, so the factory in that case would probably kind of go sort of in the middle of those three locations between the forest, the mine, and the town, right? It's going to be kind of somewhere in the middle, right? But you see how you could change the transportation costs? You could weigh them differently. What if it's really expensive to transport lumber and really cheap to transport pencil, the final pencils, and the copper's like somewhere in the middle? Let's say it's a 5:4:2 ratio, right? Do you think the factory is going to end up closer to the forest? Just naturally, it would, wouldn't it? Right? And so I've got the transportation costs here. Now, the unit for transportation costs would be dollars per kilometer, for example, right? But for you guys, with the physics and lab weights, this could be like some number of grams that's going to correspond to some weight, right? You do 500 grams, 400 grams, and then 200 grams, the lab weights, right? You guys can do that, right? And then I have 4 locations written down here. There's the location of the forest. This says forest. We got the location of the copper mine. We got the location of the town. And then finally, here's the question that's being asked is, what's the location of the factory? Okay, and you could record these locations, latitude, longitude, or what we're just going to do is Cartesian coordinates, right? X, Y, X, Y, X, Y, X, Y. You guys get that idea? X, Y coordinates, right? Right. You know what? Maybe save a little time here. Show you guys what I drew last class so you guys can see the full picture. Okay. So you guys see the lab table. This is the lab table right here. This sort of rectangular looking thing. Lab table. Okay. Now I've measured this ahead of time, and I know that the lab table is 122 centimeters wide. So that might be useful information as you guys go into this lab. 122 centimeters. You get that? Okay. And see how I have this point right here labeled 0, 0, like as the origin point. Okay. So once you've got your 0, 0 origin point mark, now you can know the locations of, well, these other 4 locations, bam, 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 with respect to that origin point, right? So many centimeters over and so many centimeters up. You guys get that? Let's look at the locations of each of these, right? And each of the inputs, so I've got the mine right here, and I've got the forest right here, right? I'm putting a pulley right at the edge of the lab table. There's the pulley that represents the location of the mine. There's the pulley that represents the location of the forest, where the wood's coming from, right? I've also got another pulley that represents the location of the town, right? Is that? And then see there are 3 strings that are tied together, right? And where the 3 strings converge, that is going to be the equilibrium point, the location of the factory. Okay. Right. So then throw on a here's the coordinates. Okay. So just eyeballing it, I see the mine is most of the with the lab table over to the right. So anyway. Let's say it comes out to like this number, like 99 centimeters over to the right and 0 centimeters up. That could be the coordinate, right? X, Y, 99 centimeters over, 0 centimeters up. The forest, well, that's 0 centimeters over and so many centimeters up. Just eyeballing it, maybe about 70 centimeters. Okay. Maybe the town is over here at, actually, I know exactly the X coordinate of the town. It's definitely 122 centimeters over because that's the width of the lab table, right? And just eyeballing this, maybe it's like about 75 centimeters up, right? So I got X, Y coordinates for each of those, right? Tie 3 strings together, loop the strings through those pulleys, hang some lab weights down here. Right? And remember, those lab weights are proportional to the transportation costs. So the more expensive it is to transport to or from that location, it's going to draw the factory closer to that point, right? And the factory is going to, well, that point's going to naturally come to some point on the lab table. And that's going to be so many centimeters over and so many centimeters up. Can you guys imagine? It's like an XY Cartesian plane, right? Oops, I meant to label my axes. Right, here's your x-axis. And here's like your y-axis going up here, right? Like x, y. Okay. So the factory looks like maybe it's about 80 centimeters over and about 60 centimeters up. Bam, right there, 80, 60. You guys get it? Right. So then once you got that, you guys can just take this page. You guys can have one of these per team and mark the locations, X, Y, X, Y, X, Y, X, Y, at each of those 4 locations. You guys get that? Okay. Right. So I started you guys off with a 5 to 4 to 2 ratio of transportation costs and therefore lab weights. Okay. So I want you guys to do that setup and then also do just make up one of your own. Make up your own transportation costs. You guys can put the pulleys wherever you want them and see where the factory is going to end up. Right, you guys got that? So you guys going to do 2 very non-frame setups. Right, this one, all the numbers are already written. That's just an example, so you can see an example. Right, this one I gave you guys some relative transportation costs. Right, and then say you guys find your own locations. Right, and the third one's pretty open. Right, it's just completely open. You can put any locations, any transportation costs. Yeah. Oh yeah. Yeah. Go ahead. Right. One last little tidbit I want to mention is, it's kind of technical detail, but you might run across this. What if it's crazy expensive to transport lumber, for example, and it's crazy cheap to transport the final pencils? Like, for example, what if this number 500 was doubled to 1,000, right? Which could be represented by 1,000 grams, which is like about 10 newtons of weight, right? So like stack on this guy. At some point, do you think it's possible that one of these weights might be so heavy that the factory is just going to be vacuumed straight into that pulley, straight there? Yeah, like if this is crazy heavy and these two are like too light, right? So how could you figure out where's that tipping point going to be where, well, you just want to go ahead and just put the factory right in the forest, right? And the answer goes back to something that you guys probably learned in maybe elementary, middle school geometry class with properties of triangles. You guys remember if you have a triangle, if you add here's just a general triangle. It's not even a right triangle, it's just some generic triangle, right? Actually, it's obtuse, doesn't it? Really big angles on there, right? But whatever triangle you make, do you guys remember that the 2 shortest legs, if you add up the 2 shortest legs, the lengths of those, they have to be greater than the longest leg, right? Here is a counterexample. If I try to make a triangle where the 2 short legs add up to less than the longest leg, well, it's not even going to make a triangle. It's going to fail. Isn't that true? Right? So this principle has to be true to make a triangle. And turns out that the same story is true making a Varignon frame. See how the 2 smallest transportation costs, 400 plus 200, add up to 600, which is greater than the greatest transportation cost? Okay, that means that there will be an equilibrium point that's somewhere on the map that's not like directly inside the forest. Okay, you guys got that? Okay. Well, that's part of it anyway. Right. All right. Any questions so far about this? All right, so I will give you guys rest of class to construct a couple of Varignon frames, record your transportation costs and locations, each of those 4 locations, and then some of these other activities we'll postpone down the line, but I'll see where I can put those in class. All right, that is our wrap on the recording, and I'll be back in the lab area helping you guys out.